The title for my talk is Seismic Anisotropy of the hanging wall bedrock in the Alpine fault. It gives us some implication to understand the damage zone of a major plate bonding fault. And before start, I want to let you pass this rock sample. Try to pay attention if there some like preferred orientation patterns within this physics sample. Yeah, it's a foliated rock, and I will also talk about the lab measurement associated with this. So before I talk about our motivation, I want to show you this breathtaking satellite image of the South Island of New Zealand. So you can somehow see there's a line separates the area covered by snow and the area that's not. And that roughly indicates the position of the Alpine fault. So it's a major plate bonding fault. It separates the Australia plate on the left and the Pacific.
Use your pointer to mark it off.
Yeah, let's see here. Yeah, here's the Australia plate on the left and the Pacific plate on its right.
And the fault is located.
Yeah, the fault you can see here. That's the line I refer to, and a standard like a cross section or a structural fault can be captured as this. So usually it has a fault core that's pretty narrow and it's surrounded by a major damage zone. And when someone walks towards both sides, further away from the fault, it will have less and less metamorphism and deformation. But this is the only standard view of cross-section of fault. But in the Alpine fault, it will be a little bit different because the Alpine fault is actually have some sort of deeping like this. But behind this kind of fault, it's actually a very complex system, and it's coupled by many aspects. So it could be hydrology, geothermal, and the mechanics. For example, in terms of hydrology, we can have observed a higher pressure that's higher than the hydrostatic case. And this higher core pressure, it will lower the effective stress, and that tends to induce earthquake or increase the potential to trigger new earthquake. And the earthquake in return, it will create new damaging and create more fractures. So this is a borehole image log from another study at this study site. And as you can see, there are different fractures oriented from all directions from this image log. And when these fractures are created, they let fluids to flow in and also will alter the local geothermal condition. And as we can see here, we have actually observed an extremely high geothermal gradient at the Alpine fault. It's higher than even 100 Celsius degree per kilometer. And normally this range will be less than 40 degrees Celsius. So it's extremely high. And overall, as you can see, all these aspects, they interact with each other. And probably a more interesting fact that motivate us to study the Alpine fault is that some paleoseismic study indicates for every 250 years, there will be a large earthquake, which magnitude is greater than 7.0 happen. And the last time it happened was more than 300 years ago. So it's pretty late in its earthquake cycle. So all of these motivate us to have a better understanding on the elastic property of the in situ rock mass and these fracture networks. And we are lucky enough to get involved with this highly and unique opportunity called Deep Fault Drilling Project 2. Here, this photo shows you the study site. You can see the track and the mountains. That's very beautiful there. And we collect some active seismic data set near the fault. And here is a base map indicate where this drilling project happened and how its position relative to the Alpine fault. Here it's a zoom in map it shows you the walk away VSP, and the red cross is the offset VS short point for the dust data. Here is a cross section shows how this drilling project looks like in this cross section view. As you can see, the borehole drills through a layer of sediment, and then it gets into the bedrock, consists of foliated shapes, portomyelinite and the myelinite. And to use this data set, it actually our goal is to have a better understanding on the elastic property of the in situ rock mass and this fracture network with a very specific aspect of seismic called the seismic anisotropy. And it simply means that when the seismic wave propagates through a media, it will travel at different velocity from different direction. And by modeling this phenomena, we are trying to have a better understand what's the elastic property of this bedrock cloud. And next, to talk about further look into seismic anisotropy, we can find some source that can contribute. First, it's the mineral itself. So most of rock forming minerals are seismic anisotropic. So this shows you the crystal structure of a pores. And when these minerals, they are aggregate together to form a rock, they can either exhibit a randomly distribution or a preferred orientation distribution. So here is just an example that these three correspond to different principal axes of pores. And the result here shows it's actually distributed pretty randomly. However, as there's a local stress regime and cause deformation of the rock, for example, the one I showed you, the preferred orientation of these minerals will actually contribute to seismic anisotropy. And if we zoom out to look at this from a even larger scale for the rock mass, when there's heterogeneity is also introduced, these void space or fractures, when they have a preferred orientation, they will also contribute to seismic anisotropy. So as you can see, there are two types of anisotropy here. One is from the intrinsic factors from the mineral. One is from the extrinsic, and that's caused by the heterogeneity. And our goal is try to obtain the elasticity of the rock mass and compare it with the intact rock, and then to further separate or distinguish the contribution of either intrinsic or extrinsic factors that to help us to have more insights on the damage and this brittle deformation. So to create and make this modeling proceed, the first task is to have a 3D geology model, and I have done that derived from a previous P-wave tomography. And that was done by a colleague also in this project. Her name is Vera Lei. She used all these surface observation to get this P-wave tomography. And by setting a certain velocity threshold, we can separate this whole 3D domain into two phases, two homogeneous phases actually. Either it could be sediments or the bedrock. So I'm not working on a tomography here. I just want to invert the bulk elasticity of the metamorphic bedrock. And as you see here, this 3D structure, and there's the isosurface. It's considered as the unconformity between the sediments and the bedrock. And this 3D model also shows you how the borehole is deviating when the drilling, trying to make it deepening towards the fault itself. And another aspect is we have to have several prototype symmetry of the elasticity in our mind. And it's the simplest case, the material is treated as isotropic. That means for all the orientation or direction, it will just be the same. We just need two independent parameters to describe it. And if there's foliation with the rock, just like the sample I let you pass by, that will becomes a transverse isotropic medium, which requires 5 independent parameters to describe it. And then if we add some additional fractures onto this background media, if the fractures is lines horizontally, it didn't further increase the order of symmetry. It also remained transverse isotropy with 5 independent parameters. And if we assume that the fractures is oriented vertically against foliation, that will be an orthorhombic media, which requires a total of 9 independent parameters. If the fractures has some deeping against the foliation, it will become either type 1 or type 2 of monoclinic. That requires more additional parameters to describe it. And because we know from the well log and the geology from the study site, and there will be definitely some fractures. And we just want to investigate how these fractures is aligned against this foliation. So only these 4 types I used for this inversion study. And here it shows you the zero offset data. So it's actually a comparison between the geophone and the depth. Because the geophone didn't cover as much as that, it's only getting to this 400-meter depth. And we can see this red line, it represents this unconformity between segments and the bedrock underneath. So after the seismic wave through that, due to the high contrast in terms of acoustic impedance, it converted to a P wave arrival and a shear wave arrival. So these 2 arrival will be the primary metrics used for this inversion. And here it shows you the offset depth data. So here at the short point of the with the Bedrock, and here is the seismogram associated with each short point. And I have to manually take from each seismogram where's the P wave arrival, where's the shear wave arrival. So a total of more than 2,000 P wave transit time and S wave transit time are taken respectively. This amount of work is acceptable to do it manually. However, to make this inversion, we have to lead and conduct forward modeling for a couple hundred times until it converts to optimize the result. And to do that manually, it's too much labor, just too intense. So I asked some help from deep learning to develop this automatically picking algorithm or a tool. So it's used pretty classic UNet convolutional neural network. On one side, it takes in the 3 components synthetic seismograph X, Y, Z, and it will output the predicted P wave arrival and shear wave arrival. And still at this point, we have almost done talking about how I formed this whole inversion workflow. So everything on the left-hand side, let's say the geological structure is from P wave tomography, and we also can know the geometry of the geology, and we have also know the sediment property from the well log, and we have 4 prototype as elasticity symmetry. I have also done manually picking from the field data for the P and S wave arrival, and everything within this dash frame means it's a fixed parameters in our numerical experiment. And everything happens on the right-hand side. It's within the numerical experiment. So forward modeling of the wave propagation in this 3D domain will look like that, shown by this animation. And I don't have time to talk about this. Actually, to make the seismic wave forward modeling in the anisotropy media, we actually need to use a different type or less commonly used type of finite difference scheme that's called rotated staggered wave. And after the forward modeling, we obtain the wave field and then use the machine learning with the picking on this wave field to get a testing or trial transit time for P and S field. Then we calculate the error between the field data and the modeling data, and then use phasing optimization to help us keep updating our elastic constant until we find optimize the size of elastic constant that's close to what we seen from the field data. And here it shows you some of the result of the elastic constant. So for 4 different symmetries, we can have some takeout. Actually, for both TI, transverse isotropic, or the orthorhombic, these numbers along the diagonal, the first three, C11, C22, and C33, they correspond to the P wave propagation velocity in 3 principal directions, respectively. And as we can see, these 3 numbers is pretty close to each other. Also, it's shown by the result from orthorhombic. However, if we look at the other 3 on the lower right-hand side corner, these 3 correspond to the shear wave velocity, and that shows much more difference compared to the P wave. That indicates we have observed a stronger shear wave anisotropy than the P wave. And directly looking at these thickness matrix may not be that straightforward, so we can plot their velocity pattern. And how to read this figure? So imagine we are working with a certain curve here, let's say the blue one, and the point along with this curve correspond to the wave propagating towards that direction. And the distance between that point to the origin, it will have a certain length, and that length corresponds to the wave velocity in that direction. So to plot the velocity pattern of these 4 models, 3 out of these 4, TI orthorhombic and monoclinic type 1, they show the very similar velocity pattern. And this monoclinic type 2 is acting pretty much different than the others. Probably tell us that the assumed geometry for this one is wrong. But all the other 3, these kind of converge to a very similar pattern. And we can also compare the result from the inversion to the lab measurement that was conducted on an intact rock. So this is from our previous colleague Wei Li. And you see the transducer is put on different sides of this rock sample, and he keep increasing the confining pressure and measure the elastic stiffness at different confining pressure. And then we can plot the result, compare the intact rock and the in situ rock mass result from the inversion for both P wave and S wave. So the takeaway actually from here is that we can observe it's pretty large gap between these 2, roughly 1/3 of the original intact rock. And this 1/3 velocity loss, it actually indicates how much damage these rocks are suffering. And next, we are also try to play with some theory to help us predict the role of fractures and how it influences the overall elasticity. So this theory is from Stromberg and Sayers. We can actually quantitatively calculate the additional contribution on the compliance matrix. And as you see, the results here show the 6 component along the diagonal. It all have some numbers associated with it. And that means not a single fracture size is capable to describe its contribution to the elasticity. And for the component of the diagonal, they are either 0 or just very small, which means these fractures may exist in orthogonal ways, which is agree with the overall image log. And here is my conclusion. So the rock mass P wave velocity reduced about 28 to 35% compared to the intact rock, and implying the extent of damage. And the 4 elastic symmetry are used for inversion, and 3 out of 4 they converge to a very similar velocity pattern. And we observed stronger shear wave anisotropy than the P wave anisotropy. And this needs further investigation. What's the reason behind that? And some preliminary fracture site analysis suggests the rock mass elasticity, it cannot be sufficiently characterized by a single dominant fractures, and it implies the fractures appear at joints, which agree with the image law. And that's pretty much it. And I'm happy to take any questions.
2 minutes for questions.
On slide 12, where you're introducing your inversion algorithm, you have quite a few inputs on different, one back
Yeah.
before that, and yeah, this one. There's well log, right? There's DAS data, there's the tomographic data.
Yeah.
How do you reconcile the well log scale with the seismic, right? There's an effective medium upscaling component to it.
Let me try to understand your question. So what do you mean is upscaling?
So from the well log data, you get on a fine scale,
Yeah,
right?
yeah.
And then your P-wave tomography is a much larger scale. So some of the layering may just become already anisotropic, but not individual layers, right? So there's a scale difference between.
Yeah. So here what I'm doing is actually to abstract the whole domain just to two phases. So for any effects from a finer scale, it didn't take into account this. Yeah. And like the segment property for just